Hi everyone, we'll start in 1 minute. How are you doing today? How was homework number 3? Which country or city are you joining from? Okay, let's begin. Today we will talk about trading simulation, but actually we will continue discussing ML modeling and switch to trading simulation later in the second part of the talk today. As usual, this course is not investment advice. Please make considerate decisions and use this only for your educational purposes. So hopefully you all know me. I'm Ivan Brigida, Business Intelligence Analyst at Google. I have educational background in computer science, finance, and data analytics. I run pythoninvest.com project, and I use all of these strategies for my own investments. So today we will cover just a few topics. First, we'll look at the comments from homework number 3. Then we'll look again at the system design view. This time we are discussing step number 4. So 3 steps are gone. Step number 4 today, and we have only one last lecture that will happen in a few weeks. Then we'll continue talking about modeling. I saw that many of you struggled during the homework, and we will use the ideas from the homework to build on them today. And I'll share the code just after today's lecture. Actually, early tomorrow, because today we still can submit the home assignment, and this code consists the solutions to the problems in the home assignment. So we will cover one more model, not just Decision Tree Classifier, but Random Forest in more detail. The interface is quite similar. It's just a few lines of code to execute it with scikit-learn library. But normally many people use Random Forest instead of Decision Tree Classifier because it is an ensemble of many decision trees. So it's a more robust version of decision trees. I also have code for a few other modeling approaches like deep neural network and logistic regression. You can look into this code as well, but I won't go deep today covering these advanced methods. And we will introduce one important principle, which is called decision rules. So we will create new predictors based on the decision rules with the higher probability thresholds. So we will take the predictions, not just a class prediction 0 or 1, whether the model predicts growth for the next 30 days, but we will take the probability predictions, some value between 0 and 1, say 0.5, which is a 50%, 0.6, which is a 60% probability, and build a decision rule just based on that probability, aiming to get a better precision. And finally, when we are happy with the models that we have, we do some simulations. So if you remember, we had simplest simulation exercise in one of the homeworks. This time we will slightly advance this simulation. The approach will be the same. We invest $100 in each positive prediction. So we have a universe of 33 stocks, 11 Indian, 11 Americans, and 11 European stocks. And every day we run predictions for the next 30 days. And if we have 20 positive predictions today, we invest $2,000 in those 20 positive predictions for the next 30 days. So it's all vector-based calculations, so you can do it very quickly in pandas data frames covering hundreds of thousands of rows. You don't need to iterate over rows, but you need some practice to do that, and I'll show you how to do that. We aim to improve our simulations, and I will be happy to see if you can do better simulations in your capstone projects. For example, and you can think of investing higher amount of money per highly positive prediction. Say one prediction today has probability of 80%, you can invest $150, and if the probability is just 60%, you invest same $100. So in this way you bet more on a highly probable predictions depending on the quality of the model. Hopefully you can achieve better results. And finally, we will continue simulations at the next lecture, and we will add even more complexity, and these simulations will be real-world simulations. So one thing that you should think of is that your capital is not endless. If we have 30 days in a row, 33 positive predictions like every day, you need a lot of capital to invest in this period of time, and maybe later in 2 months you have only 0 or 1 positive prediction. That means that most of your capital is not used. So we want to have a balanced approach that the majority of our capital is used all the time, and also if we receive some gains in 30 days when we invested it now, we want to reinvest those gains later. Or if our investments are not positive and we have some losses, we have less capital available and we need to model this. And that's why we need to iterate over rows. So it's not a vectorized calculations anymore, and we need to look one by one. It's a more complicated approach. On top of that, we will include some risk management features like stop losses, that if in this period of 30 days stock goes rapidly down, for example minus 15%, we want to sell that position straight away and not to hold it for 30 days. So it's not connected with the ML predictions, so we predicted things before, but it is connected with the trading approach and with the platform, how you want to manage your deals. So we can also discuss entry and exit criteria and portfolio optimizations as well. Say we have many positive predictions, but we decided that we don't have time to do 33 manual trades every day, and we want to invest only in top 5 stocks. How we can select those stocks so that some characteristics are met. Say the drawdown is minimum or Sharpe ratio is optimal. So that's our approach for simulations, and we'll finish with the recap of what we've learned today. So let's look again at our system. First, we discussed the different data sources, and the output for module 1 was a set of files or tables or a database from those different sources. And then we joined those sources into one big data frame. We discussed how we can clean that data, how we can generate additional features like dummy variables or date variables or something else. It can be extracting text information from earning calls as well. Then last time we introduced Decision Tree Classifier, and that was our first ML prediction for the outcome. Before that, we had only a few hand rules, which is always convenient to compare if you're doing those trading operations anyway, and you have your favorite features, your technical indicators, macro variables, anything, and you're using them. So why should you invest time in building this complex system with many features and using ML? And we aim to prove that ML predictions are better. And today we add simulations. So now there is some form of a trading system which helps us identify which records are used for trading and to simulate those trading events to get the financial result. So we are moving from ML metrics like accuracy, precision, to dollar metrics, financial results. How much would we earn in 1 year, in 5 years, etc. And finally, we will have one more discussion about automation, how you can build all pieces of this system together and deploy it somewhere and run it periodically and use it for your day-to-day operations. First, you can still join at slido.com, use hashtag SMA and add more questions. There is just one comment, that's one ticker lic.ns, not having data prior to 2022. So please add your comments or questions here or now. You can you can add comments while submitting your homework, and we will discuss a few comments today. And now let's look at the homework progression. And I compared this year to previous year. Homework number 1. This year we had 138 submissions versus 184 last year. Median time spent was 5 hours versus 4 hours last year. Homework number 2, there were 83 submissions versus 95 last year. Same 5 hours median time versus 8 hours last year. And homework number 3, as of now, we still have a few hours to submit the homework, but I ran this analysis 30 minutes ago and it was 35 submissions, and same 5 hours median time spent on homework, although some of you, I acknowledge that it can be quite challenging to solve everything, and some of you spend 9 hours or 30 hours for solving this homework. Hopefully it's all useful and you get useful skills. Let's repeat core ideas behind homework number 3 assignments. So question number 1 was generating dummies on months and week of months. Essentially, it's not very important which dummies you were generating. My goal was to teach you how you can convert categorical variables to a set of numerical variables which are called dummies. We had one particular hypothesis that 2 months like October and November are more important than others because we know there is some seasonality of earnings, of returns, and our idea here was to slightly improve those existing dummies and generate weekly dummies for every month, hoping that we can find even stronger variables, say second week of October and third week of November, predicting higher returns. And if this works, it can help you to build a better model. So you need to always think about expanding your inputs features and improving the existing features in terms of cleaning and converting them somehow to a clean numerical values. So question number 2 was to define new hand rules on macro and technical indicators. So here I wanted you to look into the existing code where I defined 2 hand rules and to define 2 other hand rules based on my educated guess from the ML model. So maybe if we add 2 more add rules, we could generate better decisions just based on those 2 rules. And the goal was to show you how to that you can generate as many rules as you want. You have a data frame, you can generate 100 more hand rules and live with those hand rules and select whatever you want. And question number 3, it had a special idea. So I wanted to prove that this ML generated prediction. So now we had a new column which was called prediction number 5 underscore CLF, which is a classifier underscore 10, which is a 10 levels deep. And I wanted to show that this specific prediction can be uniquely correct, that it is better in some way than for other hand rules. And this is one way of checking the power of predictors. You can just look at the unique correctness, and if you can build some decision, some prediction, which is uniquely correct at some subset of the data, then you're moving in the right direction. And finally, question number 4, it's a hyperparameter tuning for a decision tree. So there was a code provided how you can train a decision tree of a particular depth, like 10 levels deep or 5 levels deep. And I asked you to iterate over different depth values from 1 to 20 and find the optimal model. So today we will look at those optimizations, and we will try to select the best model. I received a few comments from you. Thank you for that. I'm reading all the comments. So most of the comments were about growing complexity and that it's harder to run the code. It takes some time. so I get it. The thing is that the real world, it's even more complicated, and we're trying to run a course which covers everything: analytics, ML, stocks, and automation deployment. So that's why we have more time between lectures, and hopefully if it's too complicated or you don't have time to solve all of the tasks, I highly encourage you to submit just half of the homework. So the commands are as following. The workflow is a bit complicated. Additional suggestion was to structure each assignment with 2 layers: a simpler foundational version versus advanced optional version. I'm trying to mark that when I have an optional version, that it's optional and it's not strictly necessary. I will try to improve. So if you have any questions on the tasks, please ask them in Telegram or Slack. You may have seen that I'm replying in Slack, and not only me, others are replying too. That if something is not working, I can try to add more comments or to make the task more clear for you. Then some people said that question 3 is hard to get exactly the same answer for the unique predictions of an ML model. Hopefully I solved everything correctly, and because I saw that some people got that number correctly. My best guess is that you need to use this setting random state equals to 42. That's the same setting that I'm using. And that means that when the models are trained, they're trained in the exact same way, and you can get the same results. There was one interesting thing, question: how do we place trade with the data in a market? I'd say that's the end goal of this course, that when you implement a capstone project, that you can run daily, not download some pre-calculated, not updated data frame with the data that I'm providing right now, but that you can call all different APIs, join the stats to the tables, maybe even save it to the database and make it incrementally. And then when you run it every day, and you will be able to predict, to make predictions to the future. Although you won't be able to compare how they worked straight away, but then if you have those predictions, you can use your favorite app or a website and place them to the trading platform. Or you can even write some code for API integration and place them automatically. And last command is that someone skipped Q3 and Q4 due to lack of advanced statistics. Hard to understand the codes. Those questions were not about statistics, although I used some of the principles from the machine learning of some of the principles for the distribution. Unfortunately, you have to read my code, which is far from being ideal. And this homework and the next homework, it extensively use the code and tries to build on this code. So now you're not coding this from scratch, but copying my Colab notebook, running it, and changing some of the pieces of it. Okay, now let's talk about time series modeling. First is when all those approaches are not always working well. you have one ML model example, which is called a logistic regression. And I was trained to be a statistician, so it's a very classic model which appeared before machine learning networks took off. And I always try to have some good baseline, some easy explainable model. So logistic regression is a simple model. It is a linear model. It is easy to interpret. It is efficient because it is fast. But when I try to change different parameters, you can see here that there are two hyperparameters, C and max iterations. I checked different values for those parameters, but the results were very similar, although they varied slightly, 52, 53, 54%, but there were no big growth combinations. So that's one example. The code is there commented for the logistic regression. We won't focus our time there. You can play with it in your free time. Second thing, that's actually what I had last year. And next slide will be about this year. And I was hoping to see the same picture this year, but it turned out that it's quite different. So last year I was trying to predict only 5 days ahead. So 5 trading days is 1 week, and the prediction for 1 week ahead has more noise, that stocks can go up and down, and average growth is just 1-2% and not like 10% that may happen in 30 days. What I saw there, that when I try to increase the complexity of a decision tree, so that's a one ML approach, same input data, but we ask a number of questions when we try to define a class. And if a decision tree has a depth of 1, we ask only one question. If it has depth of 15, we ask 15 questions. So as you can imagine, there are many combinations when you ask 15 questions versus when you ask just one question. So that's the depth. And overall, the picture here is that when you try to increase the depth, you will see that at first the model was not learning much. So it had 55% precision, which means that it was accurate about 55%. And last 3-4 years in general were quite bullish, quite positive for the markets, and it was an unconditional probability of growth. So if you randomly flip a coin and invest when coin shows heads, you will get the same 55% prediction probability. But when you had a depth of 6, and the probability jumped to 57% precision, and it was gradually increasing when the depth was 58% of precision. And then the downside of a growing depth, it means that you have so many different cases. Like if you ask, instead of 15 questions, you ask 20 questions, the size of the tree grows exponentially. It grows thousands of times. And that means that you can just tune the tree in such a way that your train data set will be perfectly tuned with the tree. So the tree will be answering questions about trained data set. But when you show to this tree that the test data set, which it never saw before, it may perform worse. And that's what we see here, that train and validation data set, that the tree is training on it, and it works well, but on a test set, on our real data, it's degrading again. And in this exercise, what we are trying to do, first we iterate over some parameters. Here we have only one parameter, which is a maximum depth. Then these parameters can be different. For random forests, it's a number of estimators and maximum depth, so we will have two parameters. For a neural network, it's hidden layers, neurons, and some other parameters. So you have some parameter space, and you try to see different combinations of those parameters which are most common, train the model on those common combinations, and see if it's performing better on a test set. Then or actually use a validation set to select the best model, and then you use just one model for the neural network, or for a decision tree, or for a random forest to compare at the test set. So if you have many different ML models, you try to select only one model per ML class and compare them at the test sets. What else you want to think about? It's a complexity of a model. We will see later today that more complex trees, they have more rules, more leaves, and more parameters to estimate. So if you have more parameters, as a rule of thumb, you need more data. So you need to see that any model actually starts learning that your metrics are increasing, and that you have enough data compared to the number of parameters. And the trade-off, again, I'll repeat this concept, that you train your set of models on a train and validation set. So you use the same train sets for say training different decision trees. You iterate over one hyperparameter max depth, and then you check on the validation set which decision tree is the best, and after you selected this the best decision tree, say over depth 15, now you know what's the best decision tree. You can retrain this model on a train and validation set just because you have more data, and hope that you get better results. And then it will be the end model that is used to predict on a test set your real world simulations. So that's what we see this time, 2025. This is a hyperparameter tuning for a decision tree predicting 30 days ahead. So it's not just 1 week ahead, but roughly 6 weeks ahead, 1.5-ish months ahead. It's more fundamental in terms of prediction goal. So we hope to see less noise. The average growth or loss may be bigger, plus 10-15%, minus 10-15%. But what we can see here is that same thing when decision trees are not complex enough, we don't see any improvement. And again, Roughly speaking, it's a very similar data set. We just have 1 more year of data, but unconditionally, there is approximately 55% of growth, including last year. And all decision trees with a complexity less than 5, they are not training well. Then there is one decision tree that shows unexpectedly high precision score, 63%. And I have an explanation for this, but we will discuss it in the very end of this lecture. So for myself, I do not really believe that this tree can be optimal enough, or I just need to acknowledge that this large data set of features is not useful, because the modeling algorithm decides to use only 5 questions and a bunch of features to ask questions about, and not 300 of them. Then we can see that there is some progress in learning higher precision score. I will use for some of the calculations a second best model of a complexity 14. Strictly speaking, it's not second best, because we have a model of depth 7 which is slightly higher, but I need some big tree, because I want to define decision rules based on a subsets of a tree. So I need some complexity in the model, so that I can further refine it into a simpler decision rules. And then again, we might see some overfitting when the model size is too big, and precision goes down again. For this model of depth 5, you can see that there are only 63 nodes and 32 leaves. Overall, it can be approximately 100 parameters to estimate, versus last year it was about 7,500 parameters. So it is 75 times easier model to estimate, and a very generalized model which uses a small subset of features. Now let's discuss the visualization approaches. I asked you to perform this in your homework. There are 2 things that you can do. First is a visual representation of a decision tree. That's the left side, and we will go slightly deeper than last time, and we will look in not at the questions asked, but at the classes generated. And the right hand side, it's exactly the same representation, but it's just more efficient. It takes less space. It's a textual representation. So first, what you see here, it's a tree with the maximum depth number 1. It is a fully connected binary tree, so that we have 2 subtrees. When we ask question, DJS 10 less than 4.8, the answer can be yes or no, true or false. And if it is true, we go left, we ask another question, and whether DJS 5 less than 0.74, and the answer is true or false. I think here it's a tree with a maximum depth 1. Actually, it has more layers. Here, it just the last level 2 with the leaf nodes, where you make decisions. It's not treated as a full as a level where you ask questions. That's probably when you have a tree with of a depth 1, but here you see the tree of a depth 2. And when we ask the second question, DJS5 less than 0.74, we will end our route into left leaf or into right leaf, and these both leaves are considered to be of a positive class, but so it will be classified as a 1, as a positive growth answer, regardless of the answer for this question. But there is a small difference in those leaves. The first leaf, it has a precision of 73%, just statistically based on the train and validation set. When you estimate this simple tree, you can see that there are almost 10,000 of true positive cases when we identified positive growth and it actually happened to be positive. But there are 3,600 false positive when we identified this leaf node as a positive, but actually it was negative. So that's why the precision is 73%, which is not bad. If we can guarantee that precision for 73%, for many of the cases, we are very happy. Then on the right leaf node, again this outcome is classified as a positive, but it is approximately 60% precision. That means that we divide 78,000 of true positive cases on 78,000 plus 51,000 of false positive, and that's how you get approximately 60% precision. So that's the visualization approach, and it builds an intuition for us when we try to define new rules based on the probability. So here at any given moment of time or for any given record, we can classify, we can show the results not as just 0 or 1, whether this leaf node is classified as a positive or a negative class, but we can send the probability, which is 0.73, 0.60 or 0.66, or for this leaf number 3 it can be 0.33. So for each leaf node we send this probability, and then you will have more information. For example, we say that we just want to select only high probable events, and let's look only at this left leaf node where precision is 73%, and let's disregard all other nodes, even if they are classified positive. And if we are missing some of the true positive decisions, we bring the overall precision on the trades that we are making higher. And that's the idea, that we select more probable events and hope that the precision goes slightly up, and it will be easier to trade on those events. So that's another visualization of our best decision tree from last year. These trees can be very big, and now the visual representation is not good enough. You can restrict the visualization. You can show only top 1, 2, 3 or 4 levels and look at the top questions. that are asked, and same thing for the text. That's how I try to debug the models and see whether these top questions are quite different, what are questions that are asked, whether it's macro variables or technical indicators or something else. So next comes random forest, and now I want to show you this code snippet number 3. So random forest. So the code here, it's commented. The approach is the same as for decision tree. We have some parameters like depth and number of estimators. Same interface. There is a class called random forest classifier where we provide number of estimators and maximum depth hyperparameters and random state, so that if you replicate this, you get exactly the same stats. We feed the model, and now there is a model, the object called ref, and when you have this model fitted, that means that your coefficients are all calculated, and now you can predict on the some subset of input data. So this is a validation set, then there is a test set, or you can predict on all data, train, test, and validation, because it's easier when you predict on all data to join this data with the input matrix and define a new column, which is called a prediction from an ML model. So there is a one cycle, or actually 2 cycles for iteration, and we try to track the best case, where it's best precision, best depth, and best estimators. That's how I got these stats. If you uncomment this code, you can print this precision matrix, which will show you exactly these results, that for 5 max depth and number of estimators equals to 10, you will get 0.5498 precision. Just for you to make the code more optimal and that you can copy it and run faster, I commented all this code and showed you these pre-calculated stats for random forest, for logistic regression, and for the neural network. Strictly speaking, this is not like a proper hyperparameter tuning, because I believe that it should be more complexity in a random forest. It's not 5, 6, 7, or 8. It should be maybe 10, 13, 15, and more estimators. That's essentially number of decision trees that are built, 10, 20, 50, or 100. Maybe it should be 200 or 500. When you add all those points, that's a lot of cases, and more complicated model will take a lot of compute time. So in this case, you might want to change a runtime type for T4 or V2 GPU and run that estimation. Or if you have a powerful laptop, you can do it as well. Here, what you can see, that's the precision score actually varies, and it shows that the simple model with the maximum depth equals to 6 and number of estimators equals to 10 is actually showing a higher precision score, 55.6%. But if you remember my previous numbers, that we have unconditional 55% of positive class of growth, that means that the model is not training well. So this is only the example of hyperparameter tuning. If you want to do the real tuning, you need to spend more time on it. So this is also a useful model type, deep neural network. So I won't go deep into neural network principles. I will just show the playground of a neural network. So you can see here one thing that you need to know, that some of the data structures can be very complex and they may be not covered with linear relations. So if you have just two variables, x1 and x2, and some defined variables on top of it, or generated x1 square, x2 square, x1 multiplied on x2, that's generated variables from just two features, and two more like sinus x1 and x2. That's input features, that's your input set. Then you have two layers, 4 neurons and 2 neurons. Then you have some parameters like learning rate, activation, regularization, and you can try to run the model. There are two types of data, blue and orange, and you can see here that model is training, and if you remove regularization here, it won't be convergent or training to show good data at all. So like that, you can see that it's quite messy. Actually, it's training here, but it won't stop. When you improve the model size, you have more features, more parameters, and it becomes more powerful, and it can converge better. It can show you better results overall. But if you show this model if you use this model on a more complicated on the data set, on the test data set, it may be too much tuned on the training and validation set, so it won't show you good results. So you need to have a lot of data to make this thing works. So you have code on a neural network in a Colab. You can check this as well. I had screencast in December last year on this, and I checked different combinations of deep neural networks. I can say that it takes a lot of time, and it's not guaranteed that you will receive any better results than your simpler baseline models. That's why I use decision trees and random forest as a main models in my course. That's another thing on this deep neural network architecture. So that any deep neural network, as I have shown you, there is an input layer, there is a hidden layer number 1, 2, or 3, or just 1, and you can calculate number of parameters that you need to estimate. This is a big neural network with 256 inputs and 2 layers. Actually, this is only one layer to 256 neurons, and then one output layer with just one prediction. But overall, it's 133,000 of parameters that you need to estimate. If you have only 10 300k of records, that's not enough. Maybe in this case you need to have at least 10 million or 15 million of records. Only then it may start working. Or you need to reduce the complexity of the model, have less layers, less nodes, easier architecture. So you have all the links here. I ask you to use either the simplest model or the model that you know more than others. Don't try to go for the most advanced models. So now we will try to work on the decision rules, on the existing predictions from a decision tree classifier. As I have shown you previously on a simple tree, for each leaf node, for each case, you have a predicted probability. It can be 48%, 40%, 60%, whatever. You need to slightly change how you make predictions. So you need to use predict_proba method from a scikit-learn library, and here you can see a distribution of predictions that you get from a decision tree. For our case, code snippet number 5. So here you can see that there are some predictions of 0, some predictions are 0.9 or 1. So it can be any number between 0 and 1. If it's a big tree, it has many cases, then it is possible that you can say 100% whether this class is positive or negative, because you just ask too many questions that you can identify all records in that leaf and say 100% whether it is positive or negative prediction. So that's the idea, that here we have a lot of 0 predictions. Some predictions are 10%, 30%, 40%, 50%, and some predictions are about 70%, 90%, and 100%. We just want to move the decision rule. So we want to say that it's a positive class, positive prediction, not only if the probability is more than 0.5, more than 50%, but higher than some threshold, some other number. And that's how you can define this threshold number. So that's it can be anything between 0.5 and 1, and there is a function that calculates this table in the code. We just iterate over different thresholds, 0.6, 0.62, etc. There are true positives. That's when we predict it will grow, and it will be growing in 30 days. There are false positives. When we predicted that it will grow, but it was not growing, so it's a false prediction. And then there are false negative and true negative. That's about class 0. We don't care much about class 0 this time, so we will look more at the true positive and false positive and try to have better precision. So here true positive 5200, false positive 4200. That's if you divide 5200 on sum 5200 plus 4200, it will be about 55% of precision. And when you increase this threshold, you may have a slightly better results. First, you have less predictions overall, say 0.92. Now it will be 7,000 total trades instead of 10,000, which it was before, and precision is 57% now. So that's how we defined new rules with 84% and 92% probabilities. They have these coding standards like classifier, best rule 84 or best rule 92. Then same idea can be applied to a random forest, which is a better version of a decision tree. In my simulation exercise, I didn't find a good version of a random forest. I need to spend a lot of time with the hyperparameter tuning to be able to find it. But I still believe that we need to use both, and it's more smooth, especially when you define these advanced rules on it. So the idea here is the same. We have some predictions. You see prediction number 5, which is ML prediction of a classifier of depth 10 that came from the last model. It has a precision equals to 59%. Classifier 5 levels deep, it has precision 63%. That came from this model, from hyperparameter optimization. Then classifier second best, that I have shown you that I use decision tree of depth 14, just something complex enough. And by default it has a precision of 59%, but if you define some rules, 84 or 92, the precision can grow. And this is especially visible for a random forest when I can change this precision considerably from 56 to 60%. So let's again look at two different decision rules. Let's assume that now we have a random forest with two decision rules. One decision rule is when the probability is more than 65%, and another is when the probability is more than 55%. So you can see here total number of trades per day. We have 33 stocks, and when the decision rule is more than 55%, you can see that a lot of times and the algorithm advises you to trade on 5, 10, 25 or even 30 stocks, just because the threshold is not very high. And when you move your threshold up, and there are many days when the algorithm says, oh, actually you need to trade only on 1 or 2 stocks, and it is easier for you if you have manual inputs for the trades, and we need to prove whether this approach is better than trade every day. One important distinction between these two cases is that you need to have a different amount of capital secured, so that before we assume that there is endless capital available for trading, but in these two cases you need different size of a capital. Say for the left hand side, you may have five trades per day on average. Let's assume that you have 30 days in a row, because there are periods when the growth is extensive, and it can be the full 1 month or 2 months when every day you have positive predictions. So every day you need to have those 5 predictions and $500 to be able to invest. that brings you to 15,000 of a total capital that you need to have to be able to execute on this algorithm for the strategy. On the right hand side, when you have a decision rule with more than 55%, you will need to trade even more, because average trade here is 90 or say 20 trades per day, and you need to have 60k of capital. That means that you will compare the gains that you get relative to the capital that you have. Say in the first case, if you earned 15,000, that means that you doubled your capital, say in 1 year, and now you have 30k after 1 year. And if you made same 15,000 in the second case, you actually brought growth of only 25% to your 60k capital. So that's the idea, that you need to be more advanced in the simulations, and that's how we gradually come to the simulation piece. Again, let's look at the code snippets. First, there was a previous code snippet when we defined more predictions. Originally there were a few manual predictions, then there were a few unchanged predictions from decision trees without any decision rules, and this time we defined a new column which had a probabilities of predictions, and we took only the second value, the second value of this tuple. That's how we got those probabilities, and then you could define conditions. Say if this vector is more than 0.84, that means that every element of the vector is more than 0.84, and then the column prediction 8 is defined as 1, as a positive prediction, and it is defined as 0 if otherwise. So that's the logics of decision rules, and that's how we got a few predictions. On top of this, just because we might change slightly the decision rules, I store a few additional columns: prob underscore prediction 8, prob underscore prediction 9. So if at some point I decide to change the decision rule and slightly increase or decrease the threshold, I will need to get access to those predictions. And now let's move on to the simulations. Let's assume that there is some prediction, say prediction number 6. That's the simple classifier of 5-level depth. There are 31,000 values for the test set, approximately 4.5 or 5 years of trading, 225 days per year. There are columns growth future 30 days and is positive growth 30 days future. That's how we know what was the exact growth. Say for this record, the actual growth was 5% in 30 days, and the positive growth was equal to 1, and prediction was equal to 1 as well. The second observation shows that there was a slight positive growth, and is positive growth is 1, but the prediction was 0. So if you want to define your financial result, you can just look at all values where your prediction is 1, where you decide to trade, and multiply on growth future 30 days. That will show you exactly what is the growth of your capital. In our case is $100 in 30 days. That's what you see here, that I define a column simulated gross revenue prediction 6, and that's an incremental growth of that initial $100 invested. Also, I introduce fees, which are 0.1% of volume for each operation. So if you buy once and sell once, it is 0.2%, and that's how you get this column as well. And net revenue, it's simply what you get from your gross revenue and what you get from the fees. So now we can move to these predictions algorithm. So this is a sample of 5 predictions for an ML model. 5 records. All records were actually positive. So you see actual growth. Then is positive growth equals to 1, prediction equals to 1, and that's why the gross growth is $12, $13, $21 based on the occasion that we have, minus 0.2. That's fees. I could say that this fees share was much higher when we were trading weekly, because it's more trades and it's a lower days than you hold your stocks, and that's the net results. And overall, for the test sets, we can say that if we trade it on all cases of this over positive prediction, we earned 66,000. We spent 3,600 on fees, and net result was 63,000. The question is, what capital do you have if you need to maintain these trades? So if you had only 50K or you had 100K initial capital, that's 2 different cases. That's why we define our final function for the simulation during this module. So the starting point is exactly the same, that there is some gross revenue 66,000, fees minus 3.7, net revenue 63,000. What else do we track? We track total number of trades. That's 18K out of 31K possible. Then we track capital required. I approximate this capital by 75%, by getting 75% quantile. This is actually quite high, like 33 trades per day. And if we assume that our model returned this 33 days per day for 30 days in a row, that means that you need to have 99K at least of a capital to be able to trade. And it also means that if it's less than that, some of the capital is not used. You're just not trading because you need to have this in your pocket. And in the end, you ended up with 161. So that's what you have, 99,000 plus 63,000 of net revenue. That's your final capital after the test set, after the test period, which is approximately 4 years or maybe even 4.5 years. And now we define metric which is used in the financial world quite often. It's called compound annual growth rate. You divide final capital, which is 1.61 thousand, on the beginning capital, which is 99,000. It's approximately 1.6 or 60% growth in 4 years. And if you use this formula, you will find that every year on average you need to return approximately 13.1%. That means that starting 100% of capital, 99,000, in 1 year it will be 13% more, in 2 years it will be again 30% more, and every year like same average growth of a capital. So it eliminates your ups and downs of your real financial performance, but it helps you to compare the annualized average growth rate for the trading strategy. So it is 13%. Let's compare this with another rule. So this is original simple decision tree rule where we have many trades, 32, 33 per day. There may be months of continuous trading, like when you simply see that all market is growing, is the biggest companies, and you can't differentiate which is growing more. You decide to invest into all of them. And the second rule is that when you're very confident in a growth, that's decision tree with a rule of more than 9.92. And that means that you have less trades. It is 14 to 19 trades per day. And now, as you have less trades, you need less capital. It's not 99,000, but 57,000 beginning capital. You can make 47,000 in 4 years. If you calculate this average growth rate, it will be 15.6%. That means that you may trade less often, but in the end, it's more efficient and you get more. And this is a very decent result. That's my final slide, which is the essence of 4 previous lectures, where we compare the financial result or simulated growth. You see the vertical axis is a simulation average growth rate. So if it's not growing, it's 1. So if you started at 1 and you're not growing, you can have still 100%. Or if you have negative growth, it can be even 0.95, so you may lose money. So you can see here that manual prediction number 3, 4, 2, they are all growing. They have a lot of trades per day. So the horizontal axis is average investments per day. So it can be 20, 25, 30. If you don't have an automatic algorithm and you need to place those trades manually, that means that you spend a lot of time doing this. But now we are proving that ML algorithms, they are bringing you additional growth. So you can see that random forest and decision tree classifier, they are getting higher growth rate and less trade, so it's more efficient. And I bet that random forest 55 rule and 65 rule, it's not optimized. I just haven't found a good random forest model which performs at least as a decision tree classifier, but I hope it should perform even better. That's what I saw last year. If you compare with the passive strategy, if you remember, during the first first lecture, I showed you different levels of growth. If you invest in a banking deposit, or if you have some passive investments like an index. Here I compare with S&P 500, which is one of the fastest growing indexes. Actually, it's top one, top two growing index in the world in the last 30 years. And you had this task in your homework that, comparing to all other capital markets, it is the fastest growing in the long term, maybe not in the moment, index. And the 30-year average growth rate for S&P 500 is 10.8%. Last 5 years it is 15.5%. Just because of a COVID, because of recent changes in the US policy, trade announcements, and many other things that happened in the last 5 years, this growth moved up. And you can see from all our simulations and ML modeling, we can get only one model that is slightly better than a passive investment strategy just in S&P 500. That probably doesn't mean that you shouldn't do it at all. It's a great challenge, and I think that you can do better. It's just you need to compare to some real benchmark, and if you select some passive approach that you invest once in a year, or maybe you slightly change every quarter when S&P 500 is changing, rebalance your investments, that's your active strategy is better. And okay, what we've learned today, we are at time. So first we discussed homework number 3. You still have a few hours to solve this homework. Then we spent a lot of time on hyperparameter tuning, on new binary classification models like logistic regression, random forest, and neural network. We found the best decision tree that you should also have in your homework, and random forests, which is not the best yet, but you might have some model of a random forest which can be even better than a decision tree, because it is an ensemble and it's an average from many decision trees. It should be more robust. It's just more time to estimate, and you need to iterate over many options before you find this good model. Then we've spoken about the decision rules, when we try to restrict more the predictions and select only high probable predictions, and sometimes it can bring a better precision. And finally, we discussed simulations. I actually want to show you the simulation piece. So that was a simple simulation where we defined just 3 columns. Then I did exactly the same for gross revenue, fees, and net revenue, and calculated average growth rate, but for all predictions. So that's the iteration over all prediction columns. I define many new columns to the data frame, and that's how I get the stats for the visualization for the last slide, where you can see the output on the fees share, on the gross revenue, on the net revenue, on the initial capital, ending capital, and average growth. I have all of that defined in one iteration, and this is stored in one function. So I will ask you to slightly extend this in the next homework, and we gradually move to my last slide. I have a placeholder for homework number 4. It will be published soon, hopefully in a few days. I understand that the material is getting more and more complicated. You won't see more complicated than this. That's the highest point. Automation model is easier. So bear with me. If you can solve just half of the homework, please submit as well. And thanks everyone for listening, and see you next time. I will update when I publish the homework, and I will publish the slides and the relevant links to the code early tomorrow, when the submission for homework number 3 is finished. See you, folks.